Hello, I'm Julien Sevron from the Joint Research Unit in Environmental Acoustics at Université Gustave Eiffel in France. I'm going to speak about the acoustical characterization of low-noise prototype asphalt concretes for electric vehicles. This work was performed within the framework of the European project LabFivia with the collaboration of Simon Bianchetti and Maria-Agnès Palas from Université Gustave Eiffel, Filippo Pratico, Rosario Fedele and Gianfranco Pellicano from University of Reggio Calabria in Italy, and Antonino Moro and Francesco Bianco from the iPool company in Italy. Let's start with the context of the study. According to the European Alternative Fuel Observatory, there is an exponential increase of electric vehicle fleet in the European area, with 3.1 million of EVs in 2020 and 10.7 of new registrations. Projection scenarios are 15 to 30% of the global market share for electric vehicles by 2030. Due to the quietness of electric motors, tire road noise is nowadays the prominent source of noise emission from electric vehicles at urban speed. Therefore, the aim of the LabFivia project is the reduction of tire road noise by proper optimization of tire road interaction. The aim of the present study is the acoustical assessment of prototype asphalt concretes which were developed for electric vehicle noise reduction within the project. The development of the low-noise asphalt concrete for electric vehicles was divided into three main steps. It was following an holistic optimization which was developed by University of Reggio Calabria. In the first step, up to 150 asphalt concrete mixtures were analyzed by the University of Reggio Calabria, and 9 mixtures were preliminarily designed and tested in laboratory. Based on these preliminary results, 2 asphalt concrete mixes were selected for prototype construction in France, in Nantes, on a reference test track at Université Gustave Eiffel. Finally, the last step is the construction of a test section in a pilot area in Florence, in Italy, based on the best mixture tested in Nantes. The present study will mainly focus on the task 2.2, which is pavement prototype construction and characterization on the test site in Nantes. 2 different mixes of very thin asphalt concrete 06 have been proposed for implementation on the prototype. As you can see in the table, both mixes are based on the same formulation, but one contained 1.9% by weight of chrome rubber. The test section without chrome rubber is named P, while the test section with chrome rubber is named PCR. The thickness of the compacted mixture is 2.5 cm, while the underlayer on the test track is a dense graded asphalt concrete O10 plus asphalt gravel. The prototype construction was performed in September 2020. It was built on the Université Gustave Eiffel reference test track in Nantes in France. As you can see on the picture, the prototype was 57 meters long and 8 meters wide. It was divided in 2 test sections, PCR with chrome rubber and P without chrome rubber. At the bottom of the slide you can compare the final state of the road surface for test section PCR and P in a frame of 20 cm by 10 cm. You can compare to test section E1, which is the reference within this study and is a dense asphalt concrete O10. Different properties influencing tire road noise have been measured on the 2 test sections. The road surface texture has been measured according to ISO 13473. It was measured by means of a 3D profilometer. Then the mean profile depth was calculated from the extracted profiles. As you can see, the MPD on both reference test sections was much lower than on the reference test section E1. it was 0.39 mm for test section P, 0.3 mm for test section PCR, and in comparison 0.82 mm for test section E1. On the right hand side of the slide you can see the texture spectra for the 3 test sections. As you can see, the texture levels of section P are up to 3 dB higher than those of section PCR at wavelengths lower than 125 mm, with an opposite situation at wavelengths greater than 250 mm. Texture levels of both prototype test sections are much lower than the reference E1, especially at wavelengths higher than 16 mm, for which a difference of about 6 to 9 dB is observed, respectively, for P and PCR. Sun absorption was also measured by means of a system conforming ISO 13472. On the right side you can see the sun absorption coefficient in 1/3 octave frequency band. As you can see, the sun absorption coefficient was quite low for both prototype test sections, with a maximum value of 0.17 and 0.26 at 2500 Hz for PCR and P respectively. The mechanical impedance was also tested on both asphalt concretes. The experimental setup is based on the frequency response function between an impact hammer and an impedance head measuring the direct force and acceleration at the impact spot. On the right hand side of the slide you can see the dynamic stiffness of sections P and PCR in the frequency range between 100 Hz and 2000 Hz. As you can see, the dynamic stiffness is almost constant over this frequency range, thus corresponding to an ideal spring behavior. Also comprising crumb rubber, it is observed that test section PCR is stiffer than test section P, with a difference up to 5 dB below 400 Hz and about 2 dB above 400 Hz. Let's turn to the acoustical characterization of the prototype test sections. Firstly, close proximity measurements have been performed according to ISO 11892. Two kinds of configuration have been tested. First configuration was a Renault Scenic fitted with Michelin Energy Saver tires. The second configuration was a Mercedes Vito fitted with SRTT tires conforming ISO 11893. Table below you can see the CEPIX overall noise levels at the reference speed of 50 km/h, corrected at the air temperature of 20 degrees. For the Michelin tire, the noise reduction by comparison with the reference surface E1 is 2.8 dBA for test section P and 2.4 dBA for test section PCR. For the SRTT tire, the noise reduction is 1.7 dBA for test section P and 2.4 dBA for test section PCR. On this slide you can see the CEPIX noise spectra at 50 kph for the 3 test sections E1, P and PCR and for both tested tire models. For both tire models, the prototype test sections P and PCR have very similar spectral shapes. The maximum spectral value for P and PCR is observed at 800 Hz for the Michelin tires and at 630 Hz for the SRTT tires. By comparison with E1, the highest noise reduction is obtained in the frequency range between 800 Hz and 2000 Hz, with a maximum of about 4 dBA at 1000 Hz. Control pass-by noise measurements have also been performed for 2 electric vehicle models. The microphone was located on the left-hand side of the vehicle at 7.5 meters from the middle of the test section and 1.5 meters above the road surface. As you can see on the left, the first configuration was a Renault Zoe fitted with Michelin Energy EV tires, and as you can see on the right, the second electric vehicle tested was a Renault Kangoo ZE fitted with Michelin Energy Saver tires. In the table you can see the CPB overall noise levels at 50 kph corrected at the temperature of 20 degrees Celsius. Noise reduction at 50 kph by comparison with the reference surface E1 is 4.2 dBA for PCR and 4.6 dBA for test section P in the case of the Renault Zoe. In the case of the Renault Kangoo ZE, the noise reduction is 3.9 dBA for the PCR test section and 4.5 dBA for the test section P. It is also observed that the Renault Kangoo ZE is about 1.5 dBA quieter than the Renault Zoe. On this slide you can see the CPB noise spectra for both vehicles, Renault Zoe and Renault Kangoo ZE. For both tested vehicles, noise spectra have a similar shape on the reference test section E1 with a clear peak at 1000 Hz. On prototype test sections, this peak is attenuated by 5 dB for the Renault Zoe and the maximum is shifted at 800 Hz on PCR test section. For the Renault Kangoo ZE, the peak at 1 kHz is reduced by 10 dBA and the maximum is shifted at 630 Hz for both P and PCR test sections. While having similar spectral shapes, it is clearly observed for both EVs that noise levels on PCR are slightly higher than noise levels on P in the frequency range between 500 Hz and 1 kHz, while the opposite is found in the frequency range above 1.25 kHz. Let's turn to the conclusions. In this study, two very thin asphalt concrete O6 have been designed and implemented on prototype test sections in the perspective of an increasing part of electric vehicles in the urban area. The very thin asphalt concrete O6 test sections P and PCR are based on the same formulation, but PCR contains 1.9% of chrome rubber per weight. Regarding the surface properties, a low MPD and texture levels was observed for both test sections in comparison with the reference dense asphalt concrete O10. A very low acoustical absorption was measured on both prototype test sections. Regarding the mechanical impedance, the PCR test section was slightly stiffer than the test section P. In terms of noise performance, the average CPX noise levels reduction at 50 kph and the prototype test sections was 2.6 dBA for the Michelin Energy Saver tires and 2 dBA for the SRTT tires. The average CPB noise level reduction at 50 kph and the prototype test sections was 4.4 dBA for the Renault Zoe and 4.2 dBA for the Renault Kangoo ZE. This noise reduction relative to the dense asphalt concrete O10 is very relevant. As a perspective, the tread pattern optimization is currently under investigation and should lead to further noise reduction on this type of road surface with very low MPD and texture levels. Thank you for your attention.